All right, well, I'm going to hand it over to our speaker, Russell.
Gonna mount this up. So hi everybody, thanks for coming out even though we are under warnings. This is my first tropical event in New Orleans, so I'm very excited. All right, thanks. It's been fun so far. So just a quick background on me. I know a lot of people here are into front end, and I don't know anything about that. And when everyone talks about JavaScript and Elixir, I always feel a little sad because I want so hard to understand, but I don't. But I'm getting there. So what I actually do most of my time is I'm a distributed systems software engineer. I work mainly on Apache Cassandra and Apache Spark, two open source projects, and I work on the integration between them. I work for a company called DataStax, and basically that's my job, is making these things work together as a product and selling it to all of our customers. So if you don't know what Spark is a tool for working with big data, and it's actually almost functionally identical in description to Apache Hadoop, so I just kind of found it funny that if I took the Apache Hadoop description and you just cross out the word Hadoop and replace it with Spark, everything else is actually still completely correct. So it is basically a software that lets you deal with huge amounts of data on lots of commodity hardware. So say you've got a terabyte of data on what tweets people have liked, and you want to analyze that. This is the kind of software that says, okay, that data is probably in some big distributed file system. You want to process it in all those computers at once. You don't want to move the data all around. You definitely can't move it back to someone's laptop, because if it's all on one person's laptop, their laptop will explode. So basically, it's that kind of system. It's a system of dealing with distributed data and doing analytics on it. So I don't really want to talk too much about the underlying primitives inside of Spark. Instead, I'm going to talk about a little bit more on the higher level abstractions that it uses that end users actually deal with. And the key one there is the Spark SQL and data frame API. So I've written a couple examples up here on the board. The topmost one probably looks exactly like any SQL query you've ever seen before. It's select count star from table. So this is legitimate code that can translate into a distributed job in Spark. And this is one of the key features, key things that drive Spark adoption, is that we have these very simple APIs, including one that looks like SQL. The second example there is something called the data frame API that is functionally equivalent. All the things you can do in Spark SQL, you can do in data frames, and almost vice versa. And then the last thing I'm showing there is an example of the old API that you aren't going to need to know too much about. But basically, the idea is that these three statements are what you as an end user using Spark has to know about. Once you know how to write those statements, it does not matter what kind of computing framework you're working on, because it can basically write the right instructions for whatever your systems you're working on. And it handles fault tolerance and all of those kinds of things for you. So key to this experience is that when we write requests like this, it's just as complicated as if you were working on a single machine with a query optimizer. There's a lot of different ways we can answer this particular question, doing a join between two tables. And in normal databases and in distributed systems like this, basically, we need some way of taking this string, which is just a description of what we want in a very high-level dialect, and we need to turn it into a plan to actually do our work distributedly. It needs to have some kind of awareness of where the data is. It needs to know the different kinds of joins it can do. It needs to know what is the most efficient way to actually do the request that's written up there. And Spark's answer to that is a framework called Catalyst. And Catalyst basically takes in this and distributes and ends up generating a plan for distributed work. And most people kind of treat this as this kind of magical operation. Who really knows what's happening inside? But, you know, it all works in the end. So what I wanted to do today is talk a little bit about how actually the inside of that works, how this query optimization actually functions, because it's, one, written in Scala, so it's got a lot of functional attributes to it. The way that it's designed uses a lot of partial function application, immutable data structures, things like that. And I find it really interesting and exciting. So let's take an example with a join like that. So let's imagine that I've got two tables somewhere in some system. Now, since I work with Cassandra a lot, I'm going to pretend these two tables are in Cassandra. I've got one table that's my OWNA-base, and I've got my DOGA-base, and obviously my OWNA-base has got owners, and my DOGA-base has got dogs, and obviously if I want to do some kind of giant analytic query on these two things, because my databases have trillions and trillions of users and trillions of pets, I need to do a join between them. So below here I've written in the data frame API, which is equivalent to that join statement I wrote before, how you would do this in Spark data frames. So basically, we load both things as data frames. We perform some filtering if I wanted to look for these specific things. And then we write in a join. And our join basically just has an expression in it which tells us which things we're joining on. We're joining on the owner on the left, matching the owner on the right. And in the end, we get a result back. But under the hood, this combination of filters and joins and all that gets handled and turned into distributed code. So how does that actually happen? So it starts out with this. So this is a logical query plan. So basically the statement we have up there, basically that Spark SQL string has to first be translated into something that the system can start working with. So if you're familiar a little with compilers or that kind of thing, we basically need to make a new tree, a tree that represents all of our requests. And in this case, it's kind of easy to see where everything's coming from. We have this join node up the top, because we need to join on this owner column. We have underneath that two sides of a tree, because we have a left side and we have a right side of our join. Our left side has the operations that are applied to the left-hand side, and at the very bottom we have this relation thing, and because we're in Spark, and it can read from both tables and files and streams and queues, this relation can be any of those things. This is basically just where we're getting our information from. And we can actually start classifying all these things because this tree is actually the internal representation. All of these nodes are physical objects in a data structure, and they're called logical nodes. We can have different classes that extend logical nodes. So for example, we have a joins, we have a project nodes, we have filter nodes, we have relation nodes. And because all of these have their own types, when we want to start changing these things around, we can write partial functions that only change certain objects based on their type signature. So for example, if we want to write a rule that only changes filters, we can just write a partial function that says take in a tree, and if you find a filter, if you pattern match on a filter and you hit a filter, replace it with some kind of different filter. So I'll show an example of how that works. But the key thing to remember about this is just a logical description of what has to happen. This doesn't say how it has to happen, because we're in a distributed system, things can be really complicated. Some kinds of joins are not possible. So on a single machine, you might think that you're bounded by RAM. You can only join certain amounts of things because you have to load both sides into memory and then you have to line them up. Things become even more complicated in distributed systems because we have that limited RAM problem on a much larger scale. And we also want to prevent moving data from machine to machine, because usually that's the most expensive thing you can do in distributed systems. You want to keep the data local as much as possible. So at this logical level, things are basically built up like this. Each node has an output, some columns that it needs to output. It's got some input, and its input is basically whatever its child is and all of its outputs. So we basically have a description of, I expect these columns to come in, these columns are going to go out. And that's what a logical node is. Inside of that, we can actually have expressions here. So this cost 11 greater than 10, that's an expression. And our expression is also a tree. Inside of this tree, we actually have cost 11 greater than 10 is actually an expression called greater than, which has two children. One child is the literal, the number 10, and the other child is an attribute reference, which is a column that we got all the way back from the bottom of our tree, that relationship. So basically, everything is trees. And all of these trees are immutable. And whenever we want to change something about this plan, we rewrite these trees. We write new trees based on our old trees. So the basic thing to remember is that our structure is input to logical node to output. And inside the logical node, we're doing something. We don't really know what. This is really just a description of what the data needs to do. It's not a description of how the data is actually manipulated. It isn't like fill up an array, take this array, do a byte shift of 5 things over. It's literally, this is a node that should filter out values that are greater than 5. We don't really know how to do that, but this is what that node should do. So when we're in this logical form, the reason that we want these high-level abstraction where we don't even say how we're doing things is we can now do sorts of analyses and optimizations that don't require us to know the underlying format of the data. So there's a lot of things that we can do in this phase. So Catalyst breaks it into 2 sets of rules. One is analysis rules and one is optimization rules. So analysis rules are built like this. So there's some unnecessary code there about how you actually get its name, but this is the core. So this is Scala. So for those who aren't familiar with, basically this is defining a method which takes in a plan of some kind of node, or some kind of tree basically, and outputs another one. And that's it. That's what every rule is. A rule is a description of how you take a tree and you generate a new tree. So there are all sorts of different ways we can then apply these rules. Inside of Catalyst, it basically lets you decide how many times is that rule allowed to be applied. Does that rule just get applied until nothing else can be transformed? In what order do you do it? Things like that. But that's not super important. There is a long list of analysis rules, but basically the analysis rules all come down to some core checks on whether or not what you're doing is actually possible. So for example, do the functions that we're calling actually exist? So if I do select count star, is count actually a thing that the database knows how to do, that Spark knows how to do? Or do the tables referred to exist? If I'm selecting from a table or a file, we probably want to check that that file is real and know what kind of file it is before we start planning out how we're going to do everything else. So here's just a couple example of some rules that I put up just so you can get a feel for what's going on during this phase. So things like resolving hints. So you can kind of hint to the engine what it should be doing in certain places. This is where it kind of takes account into that. You can check whether or not certain functions exist. You can look for references that don't exist. You can resolve references. So for example, star, as we all know, isn't a real column. Star is a representation that means all of the columns that could possibly be there. And because of that, we need to, at this point, actually resolve it into all of those different named columns. Because if we don't do that, we're going to get to the stage where we're physically planning out what we need to do, and we won't know which columns are actually used throughout the tree. So this is the stage at which we turn those things like a select star into actually select column A, column B, column C, column D internally. And here's just an example of a basic rule that eliminates unions. And this is where that partial function pattern application is really useful. So for example, this rule, eliminate unions, only does one thing. It looks for unions that contain a single element and then removes the union entirely. Because a union of a single thing is just that thing. So the rule here in Scala basically says, I'm writing a partial function here that transforms that plan. And the rule is that if I find a union object with certain children, if those children are only one, if there's only one child, then just replace it with the child. So this line right here does all of that matching for us. We don't have to take into account all of the other kinds of things that exist in the plan, because we're only writing a partial function here. We only have to cover the case that we care about. For everything else, it does nothing. So this is the kind of rules that are in analysis. And if you haven't seen, this is one of the cool things in Scala. This is that pattern matching based on the type, and then also adding a condition to the same pattern match. So anytime that there's a union and there's more than one child, this won't match. So this rule will do nothing. So optimizer rules are much more interesting. They're more about trying to think about how can we simplify the plan? How can we reorder things? How can we put filters closer to sources? How can we join things together so that it isn't as complicated to actually plan out? So some examples of that are things like limit pushdowns. If I'm requesting a limit on one side of my join and not on the other, I better put that limit way down below or wherever I can to make best of my time. if I've got two constants, if I'm doing a select where I'm selecting whether or not a column is less than 5 plus 5, well, it makes a lot more sense for me to add 5 plus 5 together and get 10 and do my analysis with it being 10 than it is for me to do it with both columns separately and continually evaluating 5 plus 5 over and over and over again. Other things like combining filters. Why do each filter one at a time when I can apply all of my filters to the same statement and have them all run simultaneously on each row as it goes through, rather than having each row go through one filter, then have a different function applied to it, then a different function applied to it, then a different function applied to it. So all of these kind of things which don't really require us knowing how we're going to do it, just that we can simplify our idea on how it actually will need to get done. So here's just a quick example of one of those rules. This is a little more complicated pattern matching from Scala. And basically, this is a rule that says if we're casting something to a type that it already is, remove the cast. Because it doesn't make sense to cast something to an int if it's already an int. So the way you can read that here, I removed the code for collection types because it's just more stuff. It's more of the same idea. But basically, we're saying that if you were looking through this plan, see we have that same thing, here we're transforming the expressions inside of those nodes instead of the nodes themselves. We're going to say if we see an expression that is casting some column to a specific data type, and that column already has the data type that we're trying to cast it to, just return that column all by itself. Forget the cast. So it starts out as cast, but just becomes that column all by itself. So basically, this is a way of removing an unnecessary operation from our work, so we don't have to do it later. So again, this only helps us figure out what we need to do to get the right answer. It doesn't tell us how we're going to do it. But after we run through these kind of optimization phases on this join that we had, it's going to look like this instead. So now we have a lot fewer nodes to deal with for our planning phase. You notice all of our filters got joined up. I don't think there's anything else too interesting here. I think it moved the filter on the right. No, it didn't. I should have made it so it went above. But if I hadn't, it would have taken the filter from above the projection and moved it below, things like that. So this is our optimized plan. But we still don't actually know how to do any work with this. So how do we actually do that? And one of the cool things about Spark is Spark also can actually push predicates into those sources that it's pulling from. So if it's reading from a JDBC source, some kind of MySQL database or something like that, and MySQL has indices on that particular column, Spark can actually push those filters into MySQL rather than running its own filters after pulling all the rows out of the data source. But it can't do that at this level. It has to actually know how it's pulling the data out. It needs to know that it's pulling the data out of MySQL to make that sort of optimization. So that leads to our last phase, which is the Spark planner. And this changes our logical tree into a physical tree that's called a Spark plan in this case. So we go from a description of what the inputs are and what the outputs are and the expressions needed to get there to a representation that actually tells us this is how we will actually pull those rows out of the database, this is how we will actually filter them one at a time, and this is how we will get the results in an iterator and pass them to the next node. So an example of this is if I'm saying I'm joining columns A and B, there's actually a bunch of different ways we can do a join in a distributed system. So one example is something called a sort merge join. In this case, it ends up writing out huge amounts of files to disks, and then moving those files around and then joining the subfiles. Each of the subfiles is sorted. It's kind of interesting, but I'll leave that for another talk. Another more easy to understand option is broadcast join, where we assume one side is very small, and if one side is very small, we just broadcast it as a hash map, and then just look up keys from the other side, because we can stream the keys through and see if there's a hash map that hits. But we can only do broadcast joins when one side is very small, and sort merge join we can do all the time. So there's a rule that says, well, in this case, you should do a sort merge join, and in this case, you should do a broadcast join. Another example is that we have these logical relations. We have this thing that says that there's a table that we need to pull data from. But we actually have to decide, so do you read that data using like a Parquet file reader, or is that a Cassandra table, and we need to actually make a database connection to pull that data in? Or is it Kafka, and we actually have to set up a broker and a consumer, and we have to have all this stuff set up to actually pull in our data? So all of these decisions are made at this planning level. This is our, how are we actually going to get the data? How are we actually going to manipulate it? So because of this, we also have one little twist here. So since all of these planning rules take a logical node and change them to a physical node, or a logical tree and change them to a physical tree, we end up with the problem that we can't actually keep applying these rules over and over and over again, because if we have an input of a logical plan and an output of a physical plan, we can't leave any nodes untouched. So the way that we do that inside of Catalyst is it actually has a special construct called plan later, which basically says I'm passing on this particular node for this iteration of the planning stage, and then wraps it in a fake physical node called plan later, and then the next rule that comes along unwraps them all and tries to resolve all the remaining ones. And basically all of these rules will just keep trying to get applied until every node has been translated into a physical node. Because unless we have a physical node for every node in the tree, there's no way to actually compute the data, because all of these nodes tell us how to actually do things, as opposed to what do we expect the output to be. So the anatomy of a Spark plan is a little similar in that it has the same, kind of nice structure here. It's got filter, we've got this set of expressions, and we've got output, but it's got a whole bunch of other classes it extends. And this is where the how really comes into play. So for example, this filter node has this as a method inside. And there's a lot of code up here, but really I want to draw your attention to this line right here, which is we're filtering that if we evaluate our predicate on this row and it's true, then we pass that row. If it's not, we don't. So basically there's literally code that it has inside, which is an if loop, or a for loop going over an if statement. So unlike our previous example, which just had these expressions and outputs, this actually has code that says if I get a row in, this is how you actually act on it to decide whether or not it's passing the filter. So the cooler part of Catalyst is not only does it have this method here, which generates, it's Scala code. So it runs a Scala function. It has all the overhead that comes with working in Scala. Objects, have to be boxed, of all that kind of type conversion and things. It also has this thing called code gen. So for code gen, instead of writing a Scala function, using a Scala function that's already been implemented, it starts building parts of a larger piece of code that will do all the work for the physical nodes in that section of the tree. So instead of having a method that's do execute and takes in an iterator of rows and does stuff to it, you actually get to generate code that gets then compiled at runtime into the method that actually does this work. So this is all done automatically, of course. As an end user, you don't have to know these things are happening. But basically, it means that when you write filter this, draw data from this source, do this operation, Spark's going to take all of that, generate small bits of Java code with mutable stuff and all of the things you need for the best performance, compile that into a new class, and then run that instead of your code. Because it can do this, because it has such guarantees on the inputs and the outputs, and it knows exactly what's happening because it has this tree that describes all of the manipulations of the data, it not only can do this, but it can also use its own representation of that data. So you might be thinking in terms of ints and floats and dates and complex UDTs and all of this, but since it has control over all of that, and it's writing the code itself, it can actually write a new representation for all of that data in pure binary, and then do bitwise operations on all of your data instead. So we can actually get out of all of that wrapping, all of those functions that we had to write, and we have to deal with Java objects being created and the JVM and all of that kind of things, gets transformed into basically these bulk operations that are done on a very low-level representation of the data that isn't even serialized into Java objects. So this is really exciting to me, and this is one of the really cool features inside of Catalyst. So again, now we basically have nodes that tell us how to process our data or how to generate a program that will process our data. So that's basically the whole gist of what Catalyst is doing under the hood when you write a query like select count star or select join one node to another. So if we look at that example that we had before, oh sorry, just one more thing. There aren't a lot of these rules. They're basically just the rules how to transform those previous nodes into actual code. Not too many of them. The only one that's important for users of our software, or the main one is, this is also where those pushdowns can come into play. Because we have a strategy that looks for a relationship and looks for filters that are above it and sees whether or not that underlying strategy, that underlying relationship can handle those filters and things like that. So that's cool. So we take our plan, once it's run through that planner, we end up with this, where now we know that there's like a sort merge join that has to occur, and for that sort merge join to occur, we need to be sorting both of those columns because we can't do a sort merge join unless we have sorted data. You know, we have these exchanges. Those are shuffles between machines to make sure that all of our data is arranged on the right machines. We have a filter, and we have a projection. A projection is renaming one of our fields because it needs it to be a string, and apparently it was an int, and I must have a filter in here that requires it to be compared against a string and not an integer. I don't remember exactly where I did that. But anyway, this is basically our end result. So this was my basic overview of how that whole system works. So if we have time, and we do, I'm going to talk about a new operation that I added to this and kind of how I did that. So one of the things about Cassandra is Cassandra has really fast key lookups. It's basically under its hood a key to wide row store. So if you're looking up things based on that key, it's very fast. It's so fast, in fact, it's much faster than if I just read out all of the data and did one of these expensive sort merge joins. So that means that if I have a lot of keys from my database, or if I'm doing a join based on those keys, it makes a lot more sense for me to just look them all up directly than it does for me to read out the entire table into Spark and then have Spark do the join for me. So how do we add a new join into this operation? So if, for example, this particular join that I've been showing before was on a column that is the partition key is what we call it, we can actually do this a lot faster without scanning those tables and letting Spark do its own thing. So instead, we want to make a new physical node, a new planned node, a new how node. And our new how node is going to basically describe what you do when you have an incoming set of keys and you want to pull those out of a Cassandra table. So it basically needs a couple things. It needs a join condition because we still need to know which keys we're pulling out. We need to know which columns we're reading out of Cassandra. We need to know how to configure that reading because the reading from Cassandra might require authentication, or it might require other parameters or throttling or things like that. And we also have to have a dependent set of nodes beneath this which actually generate those keys, because this node doesn't generate keys, it just takes keys and using those keys pulls out rows from Cassandra. So when we have this in action, basically that large plan we had before, we want it to look like this instead, where instead of having a branching join, we basically have a single table that is read out, so we get that list of all the keys we need. We do whatever filters we needed to do in that filtering, and then we use that as input to this DSE join, and then perform our join in that node instead of doing a distributed sorted merge join that requires all that network traffic. So the way we do that is we need to collapse one of our branches into that single direct join node. So up at the top we have that blue node, and basically it contains all the information from one side of this tree. And that's the side that we're looking at. So basically we take that side of the tree, we gather it all together, and once we've gathered it all together, we need to combine all of this information into our new node. So basically I've written a strategy that looks up branches that look like that are children of joins, takes all of that information and makes it into a brand new node. And that brand new node is then accompanied with planning later the rest of the tree, because the other branch we don't know how to deal with, so we have to say that we're going to leave that for other rules to take care of. And we have whatever happens before that, which we also don't know how to deal with, so that we just leave for other rules to take care of. And we end up with that single branch instead of our branching tree that we had before. So underneath the hood, this DSC join is actually a function we had already implemented inside of our connector code. So basically, we just took that code that we already provided to users in a different API and put it inside of this new node with a new strategy on when to slot that new node in and what code to eliminate when it comes. And because of that, we now have an automatic optimizer that whenever people write in joins that happen to be on partition keys, all of these changes will happen underneath the hood, and they don't even have to know about it, and they get a much better and more efficient plan. So that's really all I wanted to talk about. Thanks a lot for coming to my talk. And DataStax is almost all remote company, so if you want to join DataStax, please do. It's a great company. I like it a lot. That's about it. So if anyone has any questions, I'd be glad to answer them. Oh yeah, we have a mic up in the front. Please.
So when you were talking about the analysis and optimization phases, it reminded me a lot of the multi-stage compilers where everything is like a little micro stage. Every optimization is a different pass. I don't remember what they call multi-pass compiler or something like that. And I was wondering if that was inspired by that, and also whether you have rules that go in two directions. Because it seemed like every rule had a sort of a direction, like let's simplify this tree as much as possible, instead of like expanding every possible tree, because we might find some non-local maximum.
So this is actually, yeah, I mean, that's a great, so there's a lot of ideas here that are definitely born out of compilers, and this is an extremely old series of research. I mean, this is the kind of stuff that people have been working on in query optimizers and compilers since the 60s and 70s. Right now, there is no cost-based optimization built into this framework. There's actually a hole that they left there that can be used. So at this stage, we actually can't. At this stage, you're required to have a one in, one tree out. That tree can be bigger than the tree that you came in with, but you have one tree in, one tree out. But at the planning phase, you're actually allowed to output multiple plans. So currently, there is no cost-based optimizer inside of it. There is for some very special cases, but it's basically encapsulated. But even though you can output multiple plans, currently it always just takes the first. But eventually that is one of the ideas, is that at the planning phase, when you start actually figuring out what is the code I could write, you can write different versions, each of which has a cost associated with, and it can start assembling those together, being like, I choose this one from this particular optimization and this one from this optimization and whatever. But currently it's just you pick one or you pick none.
Right, and there's no sense of like, oh, this is actually a commutative operation, so we could reorder. It's much more like, here is a rule for reordering this particular expression.
So you can do things like that, because we can, that's actually a good example, because there's a certain class, because you can make a class, right, that has a certain parameter, and you can check whether that exists. One of the examples is foldable. So they made a class in which has a trait called foldable, and if you have a bunch of foldable things, that means that they can all be evaluated right then at that time, rather than actually going through the planning process. So for example, if an example was constant folding, if I have 5 plus 5 times 30, that's something that at that time can just be evaluated immediately. So you can do these sorts of things by adding in new nodes with new parameters and new operations, and say like, well, I've defined commutability, and therefore these things can all be moved around. There's an instance inside of this already that
but when they can be moved around, they can be moved in both directions, right? So you could factor out a constant, or you could distribute the constant.
Yeah, I mean you can still do that. Your tree can become bigger. It can have more expressions coming out of it than it came in with.
Both. That's
you can't do both at the same time yet. So again, that is not even like allowed at this stage. You can only do it the other. So there is a lot of discussion that comes into that because certain types of optimizations at further levels can only be done if you distribute rather than associate. So for example, if I'm, excuse me, if I'm doing a filter, it might make sense to distribute that filter to both sides of a join, and because both sides can actually push it down, rather than keeping that filter on the top of a join where it's only done once. So there's that kind of thing where not all the rules are written out. Yes, but unfortunately there's no cost optimization, so can't do that right now. Any other questions? Okay, I'll have to repeat it though, so it'll be recorded. So as asking if does Spark and Scala have an elegant way of dealing with the 23 tuple limit. The way they've dealt with it is Spark now runs on Scala 211 instead of 210. So there is no longer a tuple limit. Oh yeah, previously, this is relatively recent in Spark terms. This is since Spark 2.0, the default build has been on Scala 211, but before that, that was easily one of the most common issues that we had. So it helps a lot when we're in this kind of abstract, high-level abstraction where we have columns and we have our own container classes. But when we were in the RDD world, which was the previous paradigm for programming in Spark, basically the old API, that would happen a lot, where people would be like, I'm trying to build a case class that has 25 things, or I have a tuple with 30 things, and now everything's broken, and yeah. So no one dealt with that. Yeah. So the question is there a use case for using Hadoop over Spark now? Basically, the only use case I see is if you already have your data in Hadoop, or you're paying a lot of money to a Hadoop vendor which doesn't offer Spark, and I don't think there are any at the moment. So Spark has a few really big benefits, over Hadoop. And I'll start with the most basic one, is that Spark's internal representation, so this is a high-level abstraction that it uses for this advanced API. But even at a very low level, it allows for this iterative planning, basically, that lets you say, I'm going to apply this function, then this function, then this function, then this function, then this function, and then maybe cache here or don't cache here, and all these kinds of things. Where in Hadoop, you're basically forced into a pattern where you have to map, write temporary files, shuffle, reduce. Map, write temporary files, shuffle, reduce, write temporary files. So you're constantly writing to the disk in between your operations. So there's a lot of groups that try to get around this. If you're familiar with Tez and Impala, and there's a bunch of people in the Hive community that basically wrote things where they try very similar things, where you try to just shove as much as you can into the map phase and as little as you can into the reduce phase, or vice versa, so that you don't have to iterate over and over and over again. But in general, in Spark, basically when it came out on the scene, everyone was really excited because you didn't actually have to think about that. You could just say, like, if I'm doing multiple maps, if I'm doing multiple function applications, I just apply them. I just keep applying them. I don't have to think about the fact that sometimes things have to be written to disk to move them from machine to machine. It's only going to do that when necessary, whereas in writing native MapReduce code, you have to constantly be thinking about, okay, there is a network boundary every time I finish applying a function. So that was a huge benefit. Now, with this API, I mean, we kind of blow everything there out in Hadoop out of the water. It's way easier to write and use. I mean, you kind of had Hive before, but this is like, not only can we write this in Spark, but we can actually write SQL all by itself. We can write it from R. We can actually use it from Python. So there's this availability from all these different sources, including we can just connect JDBC connectors from whatever random thing we have to this system. So a lot of people are taking their BI tools like Tableau and things like that and connecting it directly to this Spark analytics engine to pull in data from different sources. And personally, from a programming perspective, so I've written connectors and things for Hadoop as well. it's just much easier to deal with. It is much easier to handle the boundary cases, much easier to know where the system is interacting with things. So it definitely picked up adoption a lot faster than I think anyone was really expecting. So, Spark basically was not a concept before 2013. And after that to today, it's now easily the #1 choice for distributed analytics. Yeah.
So the other cool thing you can do with Spark, which is totally outside of today's world, is you can integrate in the opposite direction. So I work on a thing based on Neo4j now,
Mm-hmm.
and you can actually find Neo4j stored procedures that offload work to Spark on a distributed cluster. So you can do distributed work on Spark and pull that back into the Neo4j database, and that in real time. It's like really awesome.
Yeah, for the recording, so one of the things is a lot of other systems are now using Spark as their analytics engine. So, you can be writing, I mean, this is a huge data science use case for a lot of people. The example is Neo4j. Another one is people who are data scientists working in pandas can be like, I'm doing my little work here. I've got my, oh wait, I need a different cut of my 20 terabyte data set to actually work on. Do that tiny little function call inside of Python, which calls on your huge Spark cluster, returns to you that other subset of data, and you go back to working. And you don't actually have to think about the fact that you're connecting to this giant system somewhere. So it's been really enabling of a lot of really cool work. Is that it?
I'm actually coming to the mic. I have to follow my own rules, right? Okay. So you said the people are using Spark as their analytics engine now.
Mm-hmm.
Is Spark smart enough to know that, hey, wait, this is small data, it's all on the local machine, like why even distribute this? and just not send it out over the network?
So, depending on which API you're using, yes and no. So the old API was not smart enough. The old API, if you do something that required what we call a co-group, something where data might possibly need to be associated with other data based on some feature. So for example, if I'm joining on a column, I better have all my data organized by that column, because if it's not organized by that column and separated by machine, I'm going to never be able to do my join. So basically the idea of how it would do joins is you take all your, if you imagine I'm joining names, might take all of the A data from both data sets, which might be on all kinds of different machines, move that all to one machine. So that's now my A data machine. Then the B data machine would be the next one, then the C data, and so on and so forth. So basically it would partition the data based on the thing that it knew it needed to do the join on, and then do the join locally on those machines. So it didn't know the difference between a big data that would require that and a small data that didn't require that, because it all came from one machine.
There's 10 things, they're all in the same machine, just do the join.
The new API is much smarter, but there's still tons of cases where a single machine can beat it, because it does have a lot of framework around it. There's a lot of things around this operation that you don't need to do if you start out with the assumption there's no way this will be on other machines. Everything in here basically comes in with the assumption this data is going to be broken into multiple partitions of data that are stored on different machines. I'm reading it from a distributed source, or I'm reading it from a stream that comes in at random times and is also partitioned. All these are kind of basic assumptions in how it works. So it's much slower than like basic R code if you were doing a very small data set.
Does the data stacks optimization stuff realize that, hey, these two tables, or these two relations, are actually in the same Postgres database, and it knows how to join? And so I'll just let Postgres do the join?
So we haven't done Postgres-specific joins, but there's actually, I want to say it's at IBM, there's a group that actually did this for, I'm forgetting what IBM's brand of the DB is, but their SQL-compliant RDBMS has join pushdown, where it actually will take multiple join trees and push them down. Since we work mainly with Cassandra, we're only focused on this kind of join because there is no join pushdown in Cassandra. You cannot natively do joins inside of the Cassandra database. It is theoretically possible. I mean, because you have this representation here, you know exactly what it would do, so you could write a new rule that says, I'm looking at this join, I see all the expressions that are being joined, I see that the base sources in this subtree are both, in the same database. There are also ideas, there's even more stuff, and I could go on for a long time, like ideas of if your sources can say, like, this is how I'm partitioned, this is how my data is actually already laid out on disk, and because of this, this particular operation is natural. You know, for example, if I've written out parquet files and my parquet files are partitioned on a column, then it can know that partitioning on reading and make different decisions about what it should do because it knows that you don't actually have to group data based on that column because it's already naturally grouped that way by the format. So that's the kind of thing that is kind of implemented now, but is being worked on a better interface for actually adding that kind of information in the next release. And there's lots of fun on the mailing list if you want to join in and hear about that. Cool, we're calling it. Thanks so much for coming out, and hope that I do okay in my first tropical event. So.